Thanks. So let me thanks to the organizer for the invitation. The topic of this talk will be the formation of symplectic groupoids. So this is part of my PhD thesis, and it's a joint work with João Mestre and my advisor, Ivan Struchner. So let's start. So the outline of this talk is, first, I'm going to talk about some motivation for the project, and then I will define some basic facts about the formation of symplectic groupoids. Then I will explain like Monser theorem in the context of symplectic groupoids. And for last, I will talk about some homological relations which exist in symplectic groupoids. So, first, motivation. Let me talk something about deformation theory. So, deformation theory, what is? It's the infinitesimal study of a family in a neighborhood of one of its members. So, what this means? This infinitesimal study here, this is typically made in a cohomological way. So this means that if you have a deformation of some mathematical structure, you can associate a cocycle living in a certain cohomology theory. And this cocycle has the infinitesimal information of the deformation around one of its members. This theory has been applied in a very good way in many areas. For example, we have complex geometry. There is a famous work of Kodaira and Spencer where they made the deformation of complex manifold. And they showed that the corresponding cohomology that they can associate to this case of complex geometry is a sheaf cohomology, right? Where the sheaf is something like the holomorphic vector fields on the manifold. They prove with this some rigidity and stability theorems, and they are very interesting. Another example is deformation quantization. And it's a very important topic, I think, where they try to look at the quantum mechanics as a non-commutative deformation of the classical mechanics, right? Another areas are algebraic geometry, algebra. But interesting for us in this talk will be when we apply the deformation theory to Lie theory. So this has been made in many words by several authors. For example, we have in the last century these two works from Richardson and Nienhuis, where they work on the formation of Lie algebras, morphism of Lie algebras and Lie groups. Also in the last century, a work by Guillemin and Stenberg, and some other authors about the formation of Lie pseudogroups. And more recently, in this century already, works about the formation of Lie algebroids, the formation of Lie groupoids, and the formation of Lie subgroupoids and morphism. In each one of these cases here, they found the corresponding cohomology theory. So for example, in the case of Lie algebras, the formation of Lie algebras, Richardson and Nienhuis showed that the corresponding cohomology is a Chevalier-Eilenberg cohomology associated with the adjoint representation of the Lie algebra. For Lie subgroupoids, the corresponding cohomology is the Spencer cohomology. And for these three structures, Lie algebras, Lie groupoids, and Lie subgroupoids and morphism, we have corresponding deformation complex of each one of these structures. One interesting thing about for example, the deformation complex of Lie algebroids is that in the same way that I told that for Lie algebras, the corresponding cohomology is associated to the adjoint representation, the deformation complex for Lie algebroids is isomorphic to the complex given by the adjoint representation of the Lie algebroid, which is a adjoint representation up to homotopy, right? A representation up to homotopy. And the same thing holds for these analogous things, holds for these other structures here. So, one another natural equation about a part of this is when you try to deform some geometry together with these structures. And this is one I want to tell now. This is the motivation for the work. So, let's start with the formation of symplectic groupoids. We are going to deform the symplectic geometry. In this part, I will show you, as I told, the theory of the formation of symplectic groupoids, and I will try to convince you that the corresponding cohomology associated to these types of deformations that we define is the Bott-Schumann cohomology. So, consider the groupoid G and omega multiplicative and symplectic form on the groupoid, such that the pair G omega is a symplectic groupoid. So, remember that to say that omega is multiplicative means that it satisfies this equation here. Here M is the multiplication of the groupoid, and you take the pullback by the multiplication, and this is equal to the pullback by the projection 1 plus the pullback by the projection 2 of the form, where here these are the projections. Now, to define the formation of symplectic groupoids, we want to involve both structures that we have here. We got to involve the multiplicative structure, so we want a deformation of the groupoid, and we want to deform the symplectic form. So here the multiplicative structure, the symplectic form, and we call this pair G epsilon omega epsilon. But apart of this, we need some compatibility condition, right? And of course, it's something clear what these compatibility conditions has to be. But formally, we have the definition. G epsilon omega epsilon is a deformation of the symplectic groupoid G omega if at each time, epsilon, the pair G epsilon omega epsilon is a symplectic groupoid. So that's what you expect. And at time 0, you want that G0 be equal to G as a groupoid, and G omega 0 be equal to omega. So let's see some examples of this deformation. The first example is the most trivial example, right? When you don't deform anything. So you take the constant family here. You take G epsilon here as being the groupoid always, and omega epsilon as being the initial symplectic form always. So this is the most trivial example. But there is some others interesting examples. And for this, we use symmetries to construct these examples. We can see that arising from the use of symmetries. So consider a family of diffeomorphisms of G, only diffeomorphism, such that at time 0, it is an automorphism of the groupoid. So it's a morphism with this bijective, right? When you have this, you can construct a deformation of the groupoid in such a way that you want that at each time phi epsilon be, this is the deformation that we want to construct. At each time, phi epsilon be an isomorphism of Lie groupoids with the groupoid at time 0. So, imposing this condition, we can construct deformation of Lie groupoids. And to construct the deformation of symplectic groupoids, so this has an initial symplectic form, and you only take the pullback by this, which is a morphism Lie groupoid. So if you take the pullback, it would be a symplectic form, again, on this structure. So this is the first example of deformation of Lie groupoids. But we have another type of symmetries, and they are B fields, or this is the deformation that I told. And the other type of symmetries is gauge transformation, or B fields. So consider a family of closed two forms on the base M, right? On the base of the groupoid, such that at time 0, it is equal to 0. You can deform the multiplicative form, the symplectic form, in a very natural way, simply by adding this expression here, which is the pullback by the source of the groupoid minus the pullback by the target of the groupoid. This will be symplectic. This always will be multiplicative, right? Because this is always multiplicative. But this will be not degenerate if you take epsilon small, and so in this way, this will be a deformation of symplectic groupoid. But note that these two classes of deformations always exist for any symplectic groupoid. So we want to say that this type of deformation are trivials, right? And in fact, we can put in together these two classes of sample, and it will be trivial deformation. So more precisely, formally, we have this definition. Here in red, I put, assume that we have a deformation of Lie groupoids such that the base is fixed. It's just for simplicity, but we can make the theory without this condition in an analogous way. So if G epsilon omega epsilon and G epsilon prime omega epsilon prime are two deformations of the same symplectic groupoid, we say that they are equivalent if we have this condition here. This condition here comes from what I said here, by putting together these two classes of samples, where this delta epsilon here is this multiplicative two form. And what this condition says is that basically, if you forget for a moment of this expression, you have that the two symplectic groupoids are symplectomorphic by a morphism of Lie groupoids, by an isomorphism of Lie groupoids. So this condition here says that we have at each time symplectic groupoids which are symplectomorphic up to a multiplicative B field, right? This is very natural, I think, because if we want to deform a symplectic groupoid, we have two things. We have structure on the groupoid, on the manifold of arrows, and structure on the base. So on the manifold of arrows, we have isomorphism, and on the base, we have gauge transformation. So to deform, I think is natural to involve both things, on the arrows and on the base. Now, we wonder about what's the cohomology controlling this type of deformations.
Question.
Right.
Gauge transformation is always non-degenerate, these forms.
This? Yeah, as I say, if you take if you take epsilon small enough, it would be non-degenerate, right? Because omega is non-degenerate. So what about the cohomology controlling these type of deformations? To answer these questions, we first need to look about on the deformation complex for Lie groupoids. So there is a theory which says that this complex here, which is the deformation complex of Lie groupoids, it controls the formation of Lie groupoids. And we can see this complex here as being isomorphic to the VB complex of the cotangent groupoid, where I'm saying here that there is two conventions, I think, but I'm here taking the convention that the VB complex of the cotangent groupoid it is a subcomplex of the linear differentiable complex of the cotangent groupoid. So we have here cochains which are linear with respect to the vector boundary structure of this over G. And with this way of look at the deformation complex, we can now see in a different way the deformation complex for the case of symplectic groupoids. Because we have this identification. When here we see the BB complex of the cotangent groupoid as the BB complex of the tangent groupoid by using the isomorphism induced by the symplectic form. And we have here an identification with a subcomplex of one forms on the K composable arrows on the groupoid, where this identification here with one forms, it comes very naturally from this identification, from this canonical identification of the K composable arrows of the tangent groupoid with the tangent space of the K composable arrows of the groupoid. So with these identifications, we can show how the Boltzmann complex is controlling this type of deformation. But before that, let me introduce some convention. Under this correspondence, as I said at the beginning, which every deformation, you have an infinitesimal cocycle living in some cosmology theory. In this case, if we have a deformation of symplectic groupoids, consider the underlying symplectic groupoids. So you have an infinitesimal cocycle associated to the deformation, and it lives in the deformation complex of the groupoid of degree 2. But with this correspondent, we are going to look at this psi 0 as a one form on the composable arrows. And it will be the groupoid deformation to cocycle, right? So keep in mind this because in the next slide, I think, we are going to use. So now we can talk about the cohomology, in fact. So consider the formation of symplectic groupoids. And define eta 0 as being this element, psi 0 minus omega 0 dot, which is a degree 3 element of the total complex, of the Boltzmann complex, with this. But note that this psi 0 is an element regarded as a one form. It is an element here. Yeah. It's an element living here. It's a one form on the composable arrows. And omega 0 dot is a two form on the groupoid. Another color. Yeah. This? Yeah. Yellow. It's because Y is white here. Better? So we have that this element is a element of degree 3 in this complex, which means that it lives in this diagonal of the Boltzmann complex. So I think many of you know the Boltzmann complex, but it is a double complex in which we have differentials, horizontal differentials and vertical differentials. And the horizontal differentials, all of them, comes from the simplicial structure of the groupoid. And the vertical differential are the Drummond differentials of the forms. All. and each one of these diagrams commutes. So, to say that this is an element of degree 3 means that it lives in this diagonal here. Here we have the function of the 3 composable arrows, and here we have another. And this eta 0 satisfies some properties. The first is that it is a cocycle in this complex. So this means that if you take delta of size 0, it will be 0. If you make the differential, the RAM differential of size 0, it would be equal to delta to omega 0 dot. Here we have a convention of sign. So this is the equation that we get. And if we take the RAM differential of this, it will be 0. So this means that it is a cocycle in the total complex. And apart of this, we have that the corresponding cohomology class of eta 0 depends only on the equivalence class of the deformation of the symplectic groupoid. This first thing here, that it is a cocycle, it comes from this multiplicative condition here. Because we have a family of symplectic groupoids, so we have a family of multiplication, a family of forms. And if you take this family of equations and you take derivative at time 0, you obtain that it is a cocycle in this complex. And similarly, this second condition, you take the condition about the equivalence of two deformation, and you take the derivative of time 0, and you get that the corresponding cohomology class depends only on the equivalence class of the deformation. We will call this eta 0 as the infinitesimal cocycle of the deformation. Analogously, we can define eta at each time, at time epsilon. And it would be a cocycle in the respective cohomology. Here we have time 0, but for time epsilon, we have time epsilon here. And with this, we can establish the first main result of this talk, which is the most result in the context of symplectic groupoids. So, assume you have a compact symplectic groupoid, and you take a deformation of it. So, as I told you previously, we have infinitesimal cocycles associated to this deformation of symplectic groupoids, which is a family of eta epsilon. Taking this, the result is this. If at each time this eta epsilon is exact for every epsilon, in a smooth way that later I'll tell you what this means. So we have that the deformation is trivial. And here, by exacting a smooth way, I want to say that at time epsilon, eta epsilon, it is an element like this, eta epsilon, and here we have epsilon. In every place we have epsilon. And to say that this is exact in a smooth way, it means that first it is exact. It is exact. So it means that we have elements here, alpha epsilon, x epsilon, and functions on the composable arrows, f epsilon. So this we can express as saying that there is a differential such that alpha epsilon plus x epsilon plus f epsilon is equal to the infinitesimal cocycle. And to say that it is in a smooth way means that each one of this family, alpha epsilon, x epsilon, f epsilon, is smooth. So if we have this condition, the deformation is trivial. So not the analogy, only to see the analogy with the classic Moser result in symplectic geometry, which says that if you have a compact and symplectic manifold, and you take this derivative, this is a cocycle associated, and if you have that this is exact for every time, then the deformation is trivial, which means that they all are symplectomorphic to the initial one. So they are very similar, but they have a difference here with the smoothly. This is not. But it's because in this case, we can prove that the smoothness of the transgression of the cocycle is implied by the compactness of the symplectic manifold. You can use, I know, two methods. One is by using Hodge theory, and another is by using some like an integral of some expression involving the forms. But we can use that, we can make that by assuming that the manifold is compact. In this case, we would like to have a similar theorem, but not. Yeah. That's because we are assuming that G is compact. Yeah. For that, it's important, the compactness. Right, sorry. If with this condition, this would be satisfied, I maybe not, because it is based on the deformation of Lie groupoids, and in this case, it's not possible. Yeah. So we would like to have a similar result, in this case, to imply the smoothness in the, for the symplectic groupoids from some property, from some assumption. But this is not yet done, but maybe in the future. So now let me tell you about some cohomological relations, which exist in a symplectic groupoid. So for this, let me explain the general idea that we want. So we start with the deformation of symplectic groupoids. We can think of this deformation in an infinitesimal way. So we get two things. Here we get a deformation of Poisson structures. Here I'm assuming that the base is fixed, as I told you previously. So we have a deformation of Poisson structures. And on the other side, we have a deformation of the algebroids, where we take the associated Lie algebroid to this groupoid. Let me put here to say that it is a symplectic groupoid. So we have two deformations, but they are not so independent of each other, because we can see that this deformation here is induced from this deformation of symplectic of Poisson structure. Because if we look at this deformation of Poisson structure of the induced deformation of the algebroids, we know that in a symplectic groupoid, this is always an isomorphism. So this deformation of the algebroids is induced by this deformation of Poisson structures. And this relation here, we can express this in cohomological terms. And this was made by Crichton and Murday, where they define this map here, which relates the Poisson cohomology of the base on M, which is the cohomology controlling the formations of Poisson structures. And here we have the deformation cohomology of the Lie algebroid T star M associated to the Poisson structure pi, which is the cohomology controlling the formation of Lie algebroids. By this diagram here, I'm interested in integrable Poisson structures. But in fact, this map can be defined for non-integrable Poisson structures. But in the case of integrable Poisson structure, we want some similar relation. So what if M is integrable? We got some similar relation, some cohomological relation. And so the goal is to define one map, IG, for a symplectic groupoid, which goes to the differential cohomology of G to the deformation cohomology of G, where G is the symplectic groupoid integrating this Poisson manifold. Note that this map IG is the global analogous to the map I, because here the Poisson cohomology is equal to the algebroid cohomology of T star M. And here we have the groupoid cohomology of the groupoid integrating T star M. And the same thing here. Here G is the groupoid integrating this algebroid associated to the Poisson structure. So, to define this map, we use two facts. Let me tell you some things about this map. We use two facts. The first is that we have this isomorphism between the deformation cohomology with the linear cohomology of the cotangent groupoid. This is an isomorphism only in cohomology. We don't have this isomorphism in complex, in the level of complex. We have a quasi-isomorphism, and this was made by a work of Alejandro and Thiago. And the second fact is consider this map J, which is the composition of these two maps, T, where T is a natural map that you can define, which is the tangent leaf of cochains. You take cochains of the groupoid, and it goes to cochains on the tangent groupoid. And here omega sharp is the induced map by the symplectic form. So if we compose these two maps, this J in the level of cohomology, the map J in the level of cohomology, and we compose with this isomorphism that, let me call it phi. So this will be, as read, right? This will be the map IG that I want to define, which will be this map here from the differentiable cohomology to the deformation cohomology. But now, what's the relation with the map I that was defined by Crichton and Murday? This is expressed by the next theorem. So IG commutes with the respective Van Eck maps and with the map I. In the case of G, via S-connected symplectic groupoid. So we can regard this theorem as saying that IG is the global counterpart of the map I, right? So in the last 10 minutes, I think, let me tell you some, very briefly, some steps of the proof of this theorem. So we use two facts, basically. The first step is a simple diagram. It's a simple, really, where we we separate the condition of the multiplicative of the symplectic form. We use first the non-degeneracy and the multiplicative of the form. And with this, we can form this diagram where, for example, this diagram 1 involves the map T here, the tangent leaf of cochains of the groupoid, and the tangent leaf of cochains of the algebroid. And the commutativity of this diagram, this says that it commutes with the Van Ness maps, with the respective Van Ness map, up to this canonical isomorphism. This diagram 2, it involves the isomorphism induced by the symplectic form, which is an isomorphism because it's not degenerate, and isomorphism because it's multiplicative. And they induce isomorphism between the Lie algebroids associated to these groupoids. Here is the Lie algebroid associated to the tangent groupoid. And this commutativity, it says about the naturality of the Van Ness map with respect to morphisms of groupoids. And this is also a result that it was on the literature already and was proved by Alejandro and Thiago. I saw in this paper. And this diagram tree says that this diagram tree is simply express this map induced on the Lie algebroids in terms of this tangent algebroid and cotangent algebroid. So we have here JG and theta G, two canonical isomorphisms. We can take this diagram here, and in the level of cohomology, it would be this square here, which is commutative. And here, this square is simply to look at this isomorphism that I told you. And here we can see that this cohomology is the deformation cohomology of the Lie algebroid associated. And this diagram commutes when you take here the Van Ness on the corresponding cohomologies, on the corresponding deformation cohomologies. A Van Ness type map, so it satisfies the properties that you want a Van Ness satisfies about the compactness of the fibers and so on. And the second step is to add the closeness condition of the symplectic form. So in this case, we have an induced Poisson structure on the base, and a part of that we have an isomorphism between the algebroids A and T star M, which is the algebroid associated to the Poisson structure. This is an IM2 form. This is the IM2 form associated to the multiplicative form omega. And the other fact that we want is to find an expression of the map I. So we can see the map I as this composition here, where T is the tangent leaf of multivector fields, and this dTm is the same that this dA here, but it is simply the way that you look for multivector fields on Tm as being deformations on the dual of the vector boundary here. So in this case, it's the cotangent. This map here is not hard. And this map here has the same spirit that you know, for example, in the case of manifolds. You can see a vector field on a manifold as being a derivation of the algebra of functions on the manifold. So this map, dTm and dA here, has the same spirit. So, but now we consider the linear structure underlying on the vector bundle. So with these two facts, we can form another diagram, but this simple also, which is this diagram here, where here down is the map I, but looking in the context of complex. So this T composed with this tie Tm is the tangent leaf of k multivectors. And this is the map sigma, which is an isomorphism. And we define this map theta A in such a way that this diagram commutes, and the others commutes naturally. So, looking at this diagram here on the upper side, we have in the level of cohomology here a map from the cohomology of the algebroid A to the deformation cohomology of A, which is this. So, but here we have also, previously, we had defined a map from the same source to the same target. So we have two maps with the same source and the same target. And you can prove by some computation that these two maps coincides. So, having this thing in mind, you only put together these two diagrams. This is the level of cohomology, and this is the level of cohomology. You put together these two diagrams, and we obtain the proof. Because here, this composition is the map IG, and this is the map I. And here we have the Van Ness, and here we have the Van Ness. So this finishes the proof. We have some computation behind that, but looking for up, this is the proof. So in the last 5 minutes, let me talk about some final remarks. So first, this map IG, which we define, is a map which we can define, like here, only in the level of cohomology, right? But if we would like a map between the level of complex, we won't be able to do that. But we can define a map between the level of cocycles. So you take cocycles here, cocycle of the differentiable cohomology and cocycle of the deformation cohomology, and you can define an analogous map IG. And it would be a map that satisfies also two. And the second remark is that much of this theory about deformation of symplectic groupoid, it can be naturally made also for twisted symplectic groupoids. So this, and that's all. So thank you.